In this video, we'll look at Bayes' theorem and counting rules, and these are from lecture notes 7. We'll start with Bayes' theorem here. Based on the following information, we'll try to calculate a conditional probability. Let's look at the information that's given to us. We have a loan company provides high-risk loans. They have found that 45% of the companies they have provided loans to end up failing. Okay, so that's looking at all the companies that they have provided loans to. So 45% end up failing. So we'll just plug in 45% right there, because that's what that statement is essentially doing for us here, probability of failure. Well, then they say they have also found that of the companies they provide loans to but end up failing, so they've defined the universe a little bit smaller here, of those that are failing, that have failed, 70% are service related businesses. So they have instead of looking at all businesses, they're looking at the businesses that have failed, and they found that 70% are service. So that's why I wrote that statement. Oops. There we go. And then it says of the successful companies they provide loans to. So there again, it's defined a piece of the entire set of companies. It's defining those companies that were successful. 65% are manufacturing. So that's why I wrote this out here. Probability of manufacturing given successful or not failing. And that was 0.65. Okay, now problems like this could have different statements, and you just have to figure out what's given to you. And then hopefully what's given to you, we can answer the question that's being asked. Well, in this problem it says that they've approved a loan for a company that's in manufacturing. What is the probability it will succeed or not fail? So that's why I wrote this statement here out. We know that the company is manufacturing. What's the probability it will not fail? Okay, so probability of not fail given it's a manufacturing company. Well, Bayes' theorem says, okay, if you don't have the joint probability of not fail in manufacturing and the marginal probability of manufacturing, which is the case for us, then maybe we can use Bayes' theorem. We can use this formula where we're going to flip this probability of manufacturing given not fail times not fail, because that basically gives us the joint probability we're looking for, divided by the same thing here plus another joint probability that we could calculate based on a given and marginal. Probability of manufacturing given failure times the probability of failure. So that would give us manufacturing and failure. This would give us manufacturing and not fail. Adding those two together would give us the probability of manufacturing, which is the denominator we need. Okay, so do we have that? Well, probability of manufacture given not fail is given to us, 0.65, times the probability of not fail. Well, it's indirectly given to us because we know that that is 1 minus probability of fail, so 0.55. Okay, so now we have this numerator, the joint probability. Okay, and then we actually have half of the denominator in this case, because that's going to be exactly the same. So now we got to figure out this part here, the probability of manufacture given fail times the probability of fail. Well, we've got probability of fail. What we don't have is manufacture given fail. Well, because there's only service and manufacturing, we know that 1 minus probability of service given fail has got to be the probability of manufacturing given fail. Okay, because that's just a complement. Right? So we can do 1 minus, and we've got what we need now. Now this could have been given to us directly up here, and that would have been better. Okay, but it wasn't. But we could easily find it based on our knowledge of what the complement for a given a conditional probability would be. And so now we have the probability of not fail given manufacturing. So we know the company is a manufacturing company. We now would say that the probability that it will fail, or it will not fail, I'm sorry, is 0.7259. So that's an improvement over if we just look at the any company we pick at random, we don't know whether it's service or manufacturing, we would say the probability that it will not fail is 0.55. But now, knowing that the company is manufacturing is better, it's 0.7258 that it will not fail. So that's using Bayes' theorem. And now we'll go to counting rules. And these are just basic ways of finding different the number of different arrangements that could occur under different conditions, situations. And let's just look at the possible arrangements for the order in which 10 horses are chosen for their gate position. So let's say you for some reason really want gate 4. Well, what's the probability that you would get gate 4? Well, how many different ways can these horses be arranged at random? Well, it turns out that you got 10 horses that have the possibility of going into gate 1. Let's say, just say you're assigning 1, then 2, then 3, then 4. And so first you'd have 10, then you'd have 9, then 8, then 7. So that's just 10 factorial. And in Excel you use the FACT command, and that would give you the 10 factorial. So 3,628,800 possible arrangements. So 1 out of that number would be the probability of getting a certain gate for your horse, if you're interested in a particular gate. So then, how many arrangements are possible for when 2 of 6 people are randomly selected for a committee? Well, now you're dealing with a subset, and in this case, obviously, order doesn't matter. If you're being picked for a committee, it doesn't really matter what order you're chosen in. Those 2 people are chosen in. So we have what we would call a combination. So n factorial, so 6 factorial, divided by 2 factorial times 6 minus 2 factorial, or 4. Okay, so there are 15 different ways that could happen. Okay, and then what if you had a particular identification number where you could only have a 1 or a 2 in the first digit, a 1 through 5 in the second digit, and then 0 through 9 in the remaining. So then you have, and I got carried away here, I just realized. There we go. It's a 5-digit student identification number. So you've got 2 times 5, and then you've got 3 digits remaining that can be from 0 to 9. And so 10 times 10 times 10. And so you have 10,000 possible ways that could happen. Okay? And then the number of possible arrangements that for a 7-digit product number, where it can be 1 through 9 for every digit. So now it's just you got 9 possible values, 9 times 9 times 9 times 9 times 9, depending on how many digits there are. So you just take 9 to the nth power, so 7th power in this case. So there are 4,782,969 possible ways. So the likelihood that you'll get a product number that's all ones is 1 out of that number. Okay. So then you have a fifth, well, a situation 4 in the notes. We're looking at 5 total situations, and this is the one we called situation 4. How many possible arrangements are there when order matters? So let's say that you're going to pick 3 out of 8 cities here, and if you pick A, B, C in that order, you're going to travel to A, and then you're going to travel to B, and then you're going to travel to C. Well, if you pick B, D, and A in that order, then you're going to travel to B, and then D, and then A. And so, obviously, order matters in this case when you're figuring out distance. So that's now a permutation. That's not a combination. And that allows for more arrangements that could occur, and now that order matters. So here it's essentially a combination without this x factorial. So now what you have is we've got 8 cities, so 8 factorial divided by n minus x, or 8 minus 3 factorial. So you can see there's 336 possible permutations. And I just wanted to show you that there's a simpler way to do that. There's and calculators have this as well, but there's a PERMUT command in Excel where you would put the total number and the subset, and obviously you get 336. Or you can use for a combination COMBIN. Again, you have total number 6 and the subset 2. It would be 15. So if you have any questions about counting rules and Bayes' theorem, just let me know.